All right, so our car here is got a certain trajectory on this road, and strangely, its velocity is given by this relationship here. Okay, whatever. All right, it says determine the magnitude of its acceleration. Okay, so just to review, remember what that's going to mean is we need this. Okay, so we're going to have to find the tangential acceleration and the normal acceleration, and then we'll combine them. Okay, just like that. So let's go ahead and start with finding that tangential acceleration. And so if v is 2s, okay, a is v dv ds, which means it's 2s times the derivative, which is 2, and that becomes 4s. Okay, now let's go ahead and find it, because it says when s is equal to 10 meters. Okay, so v evaluated at 10, okay, it's just going to be 2 times 10, so that's 20. And then the acceleration, once we get to 10, is going to be 4 times 10, which is a 40. Okay, just like that. All right. And by the way, this is the tangential acceleration. Okay, now let's find the normal acceleration, a sub n. Remember, it's going to be v squared over rho. Okay, and our velocity at the point of interest is 20. So we've got 20 squared. And rho up here is 50, just like that. And do the math on that, and what you get is 8 meters per second squared. Okay, so put some units on here. Meters per second squared. Okay, and there we go. Okay, so we've got a sub n to plug in and a sub t to plug in. Okay, just like that. So pretty straightforward. All right. Now we're going to look at another one where we may have to use a little trickery in order to come up with our values. All right, but again, we're going to look for an AT, we're going to look for an AN, and that's good to go. Okay. By the way, I'm recording this on Christmas Eve, and it's snowing. So how about that? Let it snow, let it snow, let it snow. All right. It's my contribution to your Christmas. Of course, it's not Christmas. You guys are way past that now. It's like you're into January. So, all right, let's look at this one. Okay, so here it says determine the acceleration. Okay, so now they didn't specifically say magnitude, but again, they don't have to tell us. We know still that what we're going to be looking at is a is the square root of AT squared plus AN squared. Okay, so we're going to be trying to find those guys. All right, now this one's a little more complicated. We got to read it pretty carefully. The car is decelerating. Okay, that's a term your book uses. In physics, we don't really say deceleration, but that's okay. So it's going to be a negative value for the acceleration, slowing down from A to C. Okay, so at A, I'm going to write this down here. At A up there, our velocity is 25, but at C, it's down to 15. Okay, and it does say decelerates uniformly, so that's nice. That means we could use Bumblebee, Sam, Optimus Prime. So in other words, it's constant. Since it's a uniform deceleration, it's a constant value. Okay, now what we don't know is the velocity here at B. Okay, so our point of interest is actually B. Okay, so let's go ahead and get that tangential acceleration. Okay, and we're going to use Bumblebee for that. 2a delta s. So do our algebra here. V final squared minus V initial squared over 2 delta S. Okay, so finally is here. Initially is here. 25 meters per second. All that's squared over 2, and our delta S is, it's 250 plus another 50. Okay, so the distance from A to C is actually 300. Just like that, okay? And that's the tangential acceleration. Once we put our numbers in there, run that on our calculator, okay, what we get is negative 0.6667 meters per second squared. Okay, there you go. It's almost the number of the beast. I don't know what that means, but could be ominous. Okay, now, in order to get A sub n, we need v squared, but at b over rho. Now we know the value of rho, it's just 300. What we don't know is vb. Okay, so, but what we could do is we can use Bumblebee again to help us out here. So we can say vb squared is v at a squared plus 2 at delta s. Okay, so if we put in our numbers there, we've got 25 meters per second quantity squared plus 2 onto minus 0.6667 meters per second squared, and our delta s is 250. Okay, now when you run the mathematics on that, okay, that's vb squared. Run all that out, make sure you take the square root. Okay, don't forget to do that. Okay, what you're going to get is 17.1 meters per second. Okay. All right, so let's plug that in here. 17.1 meters per second over rho, which is 300. And we're going to get out of that 0.972 meters per second squared. Okay, there we go. That's the 2 bits that we need. Okay, so again, we're going to stick A in up there. We're going to stick AT over here and call it a day. All righty, so now the next, I'm just going to do one more for you. Okay, because in these examples, you've seen kind of what we're up against. You got to find AT, you got to find AN. So there's going to be different ways to do that. But in the next example, we have to figure out what the radius of curvature is. Okay, so we don't always know from the question what the radius of curvature is. So we might have to work that out. Okay, so let's see how that works.